We'll just wait a few more minutes, see if somebody else joins, and then we'll begin. Okay, we'll begin. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So we'll go over the contents of week 10, and then we'll look at a few questions that will help you solve the assignments. Okay, so before that, we'll just do a brief recap of the concepts that we have gone through in, I think, 2 or 3 past lectures. So the condition for longitudinal static stability is only Cm alpha is less than 0. Cm naught greater than 0 is only to trim the aircraft at a positive angle of attack. It has nothing to do with the longitudinal static stability. Okay, so your graph would look something like this. This is the Cm versus alpha, where this is Cm naught. And we've seen that this Cm naught differs from the Cm versus Cl graphs. So the Cm versus Cl graph would have a similar pattern for a stable aircraft, for a longitudinally stable aircraft. It would have a similar pattern to that of Cm versus alpha. But this intercept here, this Cm naught 2 is not equal to the Cm naught. Okay, it would be different. Okay. Then we saw the wing and the tail contributions towards this Cm naught and Cm alpha. So we've done several questions on the various parameters and their effects. So this is the Cm naught contribution of the wing. This is the Cm naught contribution of the tail. This is the Cm alpha contribution of the wing. And this is the Cm alpha contribution of the tail. We require it to be negative. Cm alpha should be negative. So we can see that the wing does not contribute towards stability. That is why we need a tail to ensure longitudinal static stability, because this has a negative sign. The overall sign of this term is negative. Then we saw what a neutral point is. It's just analogous to the aerodynamic center of the wing. It is the CT location at which your Cm alpha is 0, right? It doesn't vary with change in angle of attack. Then we saw the definition of a neutral point. Here, we know that the static margin is dCm upon dCl, minus dCm upon dCl. Now, if you go on adding this, so if you write it, it's minus dCm by dCl per wing minus dCm by dCl per tail minus dCm by dCl per fuselage, so on and so forth. Simplifying that expression will give you this, right? We had done a couple of problems on this. So this term comes from the dCm dCl of the wing, and this is the dCm dCl of the tail. You can see that from here, okay? Okay. So we saw the static margin. Static margin is a measure of the stability of an aircraft. It is the difference between the neutral point and the CG. Larger the static margin, more stable the aircraft is. If you bring the CG to the neutral point, your static margin becomes 0 and the aircraft is neutrally stable. Then we saw the control. Control, we saw that it does not affect stability in any way. So what the control does is, this is your CM versus CL graph. The slope remains constant. No matter how much you deflect your elevator, the slope of this graph remains constant. Deflection of the elevator only changes the CM naught, or it only translates the graph. It does not rotate the graph, right? Why do we do that? To trim the aircraft at different CL trims. So initially it was trimming at this CL. Now it will trim at the new CL. That is why we deflect the elevator. Now to more stable the aircraft is, you need to deflect your elevator more to achieve the same CL trim characteristics. Okay. The convention we follow is elevator down is positive. This question was there in the forum. I just want to repeat this. Elevator down, when you deflect your elevator down, it is considered positive, right? Downward deflection of the elevator is positive. Upward deflection of the elevator is negative. Okay. Okay. When you deflect the elevator, you can say that it effectively changes your camber. So our tail initially was symmetric. And when you deflect your elevator down, that is positive deflection. This is a positive delta E. When you deflect your elevator down, it changes the camber of the aircraft. It changes the camber of the tail, right? So initially it would not have produced lift at 0 angle of attack. Now it will produce lift at 0 angle of attack. This is the physical significance of deflecting your elevator. Okay. Okay. So now when you deflect the elevator down, it produces a force. There is an increase in lift. So the CL delta E term, due to a positive elevator deflection, is positive. You can see deflecting the elevator down gives you an upward force, increase in lift. So it's positive. But this change in lift due to the positive elevator deflection gives you a pitch down moment, gives you a negative CM. So positive delta E gives you a negative CM, which is why our term here, CM delta E, is negative. CL alpha is positive, VH, tail volume ratio, tail efficiency factor, control surface effectiveness parameter, they're all positive. And you have a negative sign here, so this entire term is negative. Positive deflection of elevator, that is downward deflection, gives you a nose down moment or a pitch down moment. Okay. Then we saw what the equation for delta E trim, that is how much you need to deflect your elevator to trim the aircraft with different CLs. That is what I mentioned here. Initially, you're trimming at this CL, and then you trim it at, you want to trim it at a new CL. How much should we deflect the elevator to ensure that you trim your aircraft at the new CL? That is what this equation gives you. Again, it's a linear equation with an intercept and a slope. So the intercept is given by minus CM naught by CM delta E. And the slope is x bar NP minus x bar CG, which is the static margin, divided by CM delta E. And we need to keep in mind that this XNP is always stick fixed neutral point, never stick free. Okay. So the delta E trim governed by the strict fixed neutral point. Okay. Then there was a question in the forum. This question was from, I think, assignment 5. We had discussed this, but there is some confusion. So I thought we'll just go over this again. For a conventional aircraft, the sign of CL delta A and CN beta are respectively. Can someone try to recall what you've answered?
Second option, ma'am.
Second option, yes. So I'll just go over all of those stability and control derivatives because there seems to be some confusion still. So let's start with CM alpha, very well known. We know this. It needs to be negative. Next is CN beta. Okay, CN beta will be positive. Why? Let's discuss this. So this is, suppose this is your aircraft and you have your vertical tail here. So what is a positive beta? Is this positive beta or is this positive beta? The right or the left? 1 or 2, which is positive beta? First one, exactly. First one is positive beta. Okay, so this when the oncoming velocity changes in this direction, this is our convention. This is positive beta and this is negative beta. Now let's focus on the positive beta. When you have a positive beta here, so you have oncoming velocity in this direction. So there is a force generated, something like the lift force. You have a side force generated here, which is denoted by Fy. And since our positive y-axis is in this direction, this is your positive y-axis towards the wing, right? Since that is the positive y-axis and the force generated here is in the opposite direction, due to positive beta, you have negative Fy. This is negative, correct? So now this is the force generated due to a positive beta. And if this is your CG, will the aircraft have a positive yawing moment or negative yawing moment?
Positive, ma'am.
Positive, yes. So you have a moment that is generated in this way about the CG. This is positive Cn. That is the positive yawing moment. Your z-axis is towards the underbelly, towards down. And if you have your right hand thumb rule, this is your positive rolling yawing moment. Okay. So positive deflection of beta gives you a positive rolling moment. Hence your Cn beta is positive. We require it to be positive for a stable aircraft. If it did not do this, so suppose your aircraft is here, it encounters a positive beta. Now, because our aircraft is stable, it generates a restoring moment and this beta becomes zero. This positive beta is negated, it becomes zero. If this positive or restoring Cn moment was not there, then your aircraft would not be laterally stable. Okay, so the condition for lateral stability, just like longitudinal stabilities, condition for longitudinal stability, Cm alpha should be less than 0. Condition for lateral stability is Cn beta should be greater than 0. Next, let's go to the other axis, that is the rolling stability or directional stability. Okay, this was directional stability, rolling is the lateral stability. So that is denoted by Cl beta. Should this be positive or negative?
Positive.
Positive. Are you sure? Okay, let's look at it. Let's look at it. Due to a positive beta, your right wing, so this is the, imagine this is your wing, okay? So this sees a higher angle of attack. So it generates, so this sees a higher angle of attack, right? Right wing sees a higher angle of attack. So this generates more lift than this wing, okay? So it is rolling towards the left. But our convention is that roll right is positive, correct?
Yes, ma'am.
Yes. So you can also see that this Fy generated. So if I see from the side, how would I show that? Okay, so this Fy is generated at some distance from the CG. Okay, so there is an Fy term here. Okay, this produces a rolling moment, correct? This is negative Cl. So the negative Fy produces negative Cl. That means a positive beta produces a negative Cl. Okay, so that is negative. So this is as far as the stability derivatives are concerned. Now let's look at the control derivatives. Okay, so the first one was Cm delta E. Was this positive or negative? If you deflect your elevator down, will it generate a pitch up or pitch down motion?
Pitch down, ma'am.
Pitch down. So your Cm delta E is negative.
Negative.
So we just discussed this. This is your tail. You deflect your elevator down, lift force is produced. This generates a negative Cm. This is a positive delta E. I repeat again, the downward deflection of elevator is considered positive. That is our convention. Okay. Okay. So a positive deflection of delta E gives you a negative pitching moment. So your Cm delta E is negative. Next, let's do Cn delta R. Okay. Now let's look at the delta R convention. That is the rudder deflection. Okay. So if you have Bear with me. If this is your rudder, it's part of the vertical tail. Okay, I'm really bad at this. Okay. Now, if you deflect your elevator towards this side, that is towards the left, this is considered positive rudder deflection. This is positive delta R. Okay, deflecting towards the left is positive rudder deflection. Now, if I deflect the rudder towards left, that is positive rudder, will it create a positive or negative yawing moment? Will Cn be positive or negative? When I deflect my rudder this side, the side force is generated towards left or right?
Towards the right.
Correct. So you have Fy generated here. This is positive Fy, okay, because our y-axis, like I mentioned here, y-axis is positive towards the right. So Fy here is positive. Now, if this is your CG, just like the previous case, will it generate a positive or negative yawing moment? Will Cn be positive or negative? So this is the force that you've generated. What is the moment about CG?
Will be positive.
It will be negative, right? So this is the moment. This is Cn. And our z-axis is downwards. So right-hand thumb rule, it's negative, right? We just saw that this is the positive Cn. So this is the reverse of that, correct? This was positive Cn.
Yes.
So this will be negative, yes. So this is negative Cn. So Cn delta R will be less than 0. Positive deflection of rudder, that is left deflection of rudder, gives you a negative Cn, gives you a negative yawing moment. So your Cn delta R is negative. Now let's look at the last one, that is Cl delta A. Now the convention is right aileron up, left aileron down is positive. So let me just write that. Positive delta A is right aileron up, left aileron down. Okay, this is positive aileron deflection. That is the convention. Now, if this is my right wing and this is my left wing, if I deflect the right aileron down, will the lift on the right aileron increase or decrease? If I deflect the right aileron up, will the lift increase or decrease on the right wing?
Decrease.
Decrease. So let's just denote it by a small L. And similar to that, if I deflect the left aileron down, lift will increase, right? So you will have a larger lift here. Now this is your CG. It will produce this moment. This is CL. This is CL positive or negative? Your x-axis is towards the nose of the aircraft. Okay, so use your right hand thumb rule and tell me, is it a positive roll or negative roll? Is CL positive or negative? This is for positive delta A. Okay, it produces this moment. This is the CL that is produced by a positive aileron deflection.
Ma'am, the aircraft is banking right.
Aircraft will roll.
Okay, then it is positive. They're rolling.
It is
Okay.
positive, correct. Roll right is positive because your thumb will point towards the x-axis, which is towards the nose, and the direction where your fingers curl is rolling right. So that is your positive roll. So positive delta A, positive aileron deflection, gives you a positive rolling moment. So your CL delta A is positive. Okay. So these are your 3 stability derivatives and these are your 3 control derivatives. So I hope all confusion is clear now. Somebody had brought this up in the forum, so I just thought we should go over this. Keep this in mind. You don't have to memorize it. You can just draw the diagrams and see for yourself. Just remember that the axis, x-axis points towards the nose, y-axis towards the right, z-axis towards the underbelly. towards the bottom. Okay, then you can use your right hand thumb rule to find out the positive rolling moments. Then positive beta is towards the right, rudder deflection left is positive, and aileron, right aileron up, left aileron down is positive. These three things, just remember, let's write that down. Positive side slip angle is towards the right. Positive rudder deflection is left. Positive delta A is right aileron up, left aileron down, which creates a positive rolling moment. Okay, so these three things, if you remember, you will be able to find out the derivatives. Cm alpha and Cm delta E, we have done enough number of times, so there should be no confusion. For the other terms, you can just use these. If you remember these conventions, you will easily be able to get the sign. Okay, so I hope all confusion is clear now. Let's go on to the assignment questions. So this question, where they've given you Cm versus Cl at different elevated deflections. Just like we had mentioned before, the slope doesn't change when you deflect the elevator, only the Cm naught values change. Okay, it's basically to trim the aircraft at different CL trims. So now they've also given you the weight of the aircraft. They've given you wing area and the CG location. Okay. Now they've asked you to find out the neutral point. How will we proceed? First you find out the slope, right? How will you find out the slope? Take any 2 points and find out the slope. Correct? So the slope is basically the static margin. Static margin is minus DCM on DCL, which is X bar NP minus X bar CG. Okay, so now let's find out the slope. Minus DCM upon DCL. Okay, so DCM, let's take this point, this point. Okay, so that would be 0 minus of that value will be minus. Okay, let's just calculate this. So the Y scale, let's find out the Y scale first. Okay, so there are 5 markings between these two. So you have minus 0.15 minus of minus 0.2 by 5. So that would be 0.01. So each unit, each marking corresponds to 0.01 units. So now if I were to take this point here, that would be, what would it be? It will be, it's minus 0.15 and 3 units below. So it is minus 0.15 minus 3 units below that. So 3 into 0.01. Right? How much would that be?
Minus
Sorry? Minus 0.1.
minus 0.18.
Minus 0.18. I just put that here. Minus 0.18 and take DCL. DCL would be 0. That is 0 minus 1.2. So that would be
Approximately 0.15.
3.15 and X bar NP minus XCG is 0.3. So your X bar NP would be 0.4.
0.45.
0.45. Okay. Now the next question, again, I think there was a mistake in the option in the answer. So the most aft location of center of gravity will be most aft. It should have been mentioned clearly that most aft for a stable aircraft, for a statically stable aircraft. So that limit would be the neutral point. So that was not mentioned there. So the most aft location of center of gravity would be just before the neutral point. It cannot cross over because then it would be unstable, and at neutral point it will be neutrally stable. So you just put the value of neutral point. There is a mistake in the answer. I have pointed it out. They should hopefully rectify it. So here it would just be x bar NP, which is 0.45. Okay. The most aft center of gravity, that is center of gravity location that is permissible for a statically stable aircraft. That term should have been mentioned to make the question less ambiguous. Okay. Let's go to the next question. If a pilot wants to fly at a speed of 38.52 meter per second in trim condition, what will be the trim lift coefficient? Very simple question. The lift equation that we know. Lift is half rho v squared SCL. And they've given you the velocity at which you want to trim. So CL trim would be, you take lift equal to weight. Okay, at trim, lift equal to weight. So you take 2W by rho S V squared. That will be 2 into 1, 2, 4, 5, 1, 5, 5, S 075, and V is 38.52 square. So what would this value be?
0.787.
0.787. Now, next question. Similar to the previous case, if you want to fly at a speed of 34.2 in trim condition, how much would you have to deflect the elevator? Follow the same process to first find out CL trim and then we'll go for the elevator deflection. Okay. So CL trim again. 2W by rho S V square. So just substitute the values and let me know what the answer will be. Five, 0.75. 34.2 squared. How much is this CL trim?
0.999.
Okay. Now there are two ways to do this. One is since the graph is given to you and you take this approximately equal to 1, you can just draw two straight lines. So just draw something like that. And at trim, you take 0. So you draw that line like that. So the point where it coincides is the red line. And the elevator deflection there, I believe, is 15 degrees up, correct? So
Yes.
delta E is 15 degrees up, and up we know is negative. So that is minus 15 degrees. Now, if you're unable to do this graphically, you can also try to find out the CM naught. So delta E deflection changes to CM naught. So you take those 2 points, that is at 0 CM and 0 CL, substitute it in the slope equation, find out CM naught. Okay, then you can easily find out which line corresponds to which CM naught. So let's just do that. So if I take the slope, it is DCM on DCL. Take the 2 points where moment is 0, CL is 0. Okay, so where moment is 0, it would be, let me just write CM. So CM1 minus CM2 by CL1 minus CL2. First point where moment is 0, 0 minus. So the point where moment is 0, CL will be CL trim. CL trim. The point where CL is 0, CM will be CM naught. Correct? Okay, so just substitute these values. Our slope was, the slope 0.15 minus 0.15. Minus 0.15. Now let's substitute the values. That will be 0 minus CM naught by CL trim is approximately 1 is equal to minus 0.15. So your CM naught is 0.15. Now from this graph, you can see that the CM naught value is 0.15 for the red line, which again gives you the same delta E, that is 15 degrees up. Okay, so you can either draw this, which is fairly simple, drawing those two straight lines, but if that is confusing or the graph is not clear, you can go ahead with this method. Take the 2 points, one where CM is 0, which is trim, and one where CL is 0, which will give you CM naught. Okay, 2 points are where CM is 0, there CL equal to CL trim, and where CM equal to CM naught, CL equal to 0. Okay, so these are the 2 points. Point number 1, this is point number 2. Find the slope at these 2 points to give you CM naught, and then you can see which line corresponds to which intercept. I find this little more reliable, so I just shared the two methods with you. Okay. If suddenly the weight of a 15 kg payload is dropped in flight and the pilot wants to fly at same speed of the previous case, that is 34.2 meter per second in trim condition, will the elevator deflection will be less or more, or will remain same, or you cannot say. So follow the same process. Again, take the slope, dCm by dCl, take the 2 points, but your weight, so CL trim would have changed, correct? CL trim is 2W by V square. V is same, but your W has changed. CL trim in this case would be little less than 0.999. Now if I put this back in the main equation, that is not 7 minus 0 equal to minus 0.15, you get CM naught as slightly less than 0.15. So you get something around 0.14, okay? So that is somewhere here, right? So that will be a magnitude of less than 15 degrees, right? So the amount of deflection required would be less. You don't have to deflect it 15 degrees. You will deflect it a little less, okay? So if you reduce the weight in flight, the elevator deflection required to trim at the same CL at the same velocity would be less. If you're trimming at the same CL, then it would be the same thing, okay? So since they've said trimming at velocity, that meter per second velocity, that's why your CL trim changed. The CL trim is the same, the elevator deflection is the same. Okay. Okay, so now let's look at some other questions. Just look at all the value that is given to you. Using the following information, please answer the following questions. The aircraft used is a civilian aircraft with pure turbojet. They've given you Mach number of 0.6. They've given the load, that is 1,000 pounds, and plus 4 crew members at 800 pounds. The aircraft loiters between points 3 and 4 for 2.5 hours, and between points 5 and 6, that is here. This is one loiter period, this is one loiter period, for 6 hours, 30 minutes. And they've given you L by D max. Okay, all of these values here are the SFCs, okay, fuel consumptions. Okay, so just look at the flight profile. You have a takeoff, you have climb, it cruises at some for some range, and it loiters for some duration, then cruises again, loiters, cruises, lands. Okay, so this is your flight profile. Now let's look at the questions. Find the weight fraction between 0.2 and 0.3, that is W3 by W2. So in the lectures, we had seen some formulae, some direct formulae for the fuel fraction that is different for the cruise condition, different for loiter. So between points 3 and 2, are we, what is it, cruise or loiter? Cruise. So what was the formula for the weight fraction? W3 by W2 is e raised to
minus RC by the L by.
L by D. Okay. So in this case, your R is 1035. Sorry, 35433 feet. C. SFC is, what is the value here? What is the value of C here?
and 9.
0.9. Exactly. So it is a pure turbojet and we are in cruise, so it is 0.9. Okay. And this is in per hour. So we need to convert, this is in per hour. We need to convert it into per second. So just divide by 3600. You get, must you get 0.00025 per second. Then what do we need? We need V. How do you calculate V? How would we calculate V? Look at the data that is given to you. How would you calculate V?
M.6 is given.
Yes, M.6 is given to you. So how do you calculate velocity from that? V by speed of sound is M, right? So V is M into speed of sound. So M is 0.6. A speed of sound in feet per second. How much was it?
994.8 feet per second.
That comes to 596.88. That's 596.88 feet per second. Okay. What is L by D?
60.
0.866 into L by D max.
Correct. For a turbojet, it is 0.866 into L by D max. Correct. So that would be 0.866 into 16, which is
13.8.
13.8. Now plug in all of these values and tell me what is W3 by W2. E raised to minus 0.3 into S is 0.0, C is 0.05 by velocity is 96.88. 14.856. So what is this value? Calculate and let me know.
.96.
0.969. So that is this. Okay, so we've got W3 to W2. Next, weight fraction between 0.3 and 0.4 is W4 by W3. What is the equation? E raised to
minus E into factor upon L by D.
1
L by D.
upon L by D max, right? For loiter, by D max. Okay.
Yes.
So let's just substitute the values. E is 2.5 hours, convert it to seconds. 0. How much would that be? thousand seconds. C, how much is C?
0.8 amp.
8, correct. So it's still a turbojet, but it's loitering, so it's 0.8. And L by D max is directly given to you. Right, that's is 16. So what is W4 by W3? What is the value? What is the value?
It's coming on 0. Yeah, we're checking.
Okay, one mistake that we've done here is C is again in per hour. Need to convert it to per second, so it's 0.8 by 3600. That is 100,022 per second. Now plug it in and let me know.
Point eight.
0.88. Okay. It's 0.88. What is this? Weight fraction between points 4 and 7. How do we go about doing this? We take individual weight fractions and then multiply them. Okay. So first we start with W5 by W4. 5 and 4 is cruise. So it is e raised to minus RC V L by D. So what would it be? E raised to minus R is 2070866. C is for cruise 0.9. 0.9 by 3600. Divided by V is, how much did we calculate V? 596.88. 5, 6, 8, and this was 13.856. And what is this value? Then after that, we calculate W6 by W5. You tell me this quantity. W5 by W4. Now W6 and W5, W6 by W5, what is the equation? E power. It's loitering, right? So it's minus
AC L by D.
L by dx. That will be power minus, it's 30 minutes. Loiter is 0.8. Divided by L by dx, 16. This is 0.975. Okay. Lastly, we have W7 or W6. And again is cruise. So what will the value be? It's cruising for the same range.
Yeah. 0.93.
So it's 0.939. So your W7 upon W4 will be multiplying all of these. W5 by W4 into W6 by W5 into W7 by W6. That is 0.939 into 0.975 into 0.939. That would come out to be
-85.
sorry, I didn't hear you. 0.85.
859.
Right, so it's 0.859. Lastly, between 0.6 and 8. So if you have W8 by W6, you have W7 by W6 into W8 by W7. Now W7 by W6 we already have 939. We need to find out W8 by W7. So what would this be?
0.995. It's already given.
Given 0.995. So you just substitute that there. You get the value as 0.934. Right? Now we'll just go over a few concepts. Hinge moment. So your elevator is attached to your tail at some point, right? So that point is hinge and it rotates about the hinge. So if you were to deflect your elevator down, it would rotate about the hinge moment, hinge point. So the moment that the hinge experiences is given here, half rho v square SECE, that is area of the elevator, the chord, mean aerodynamic chord of the elevator. CH is the hinge moment coefficient. Now again, we represent this in a linearized fashion. So you have CH is CH naught, CH alpha T into alpha T, where alpha T is the angle of attack seen by the tail. CH delta E into delta E, where delta E is the deflection, elevator deflection. Delta T is the deflection of the trim tab. Okay, so now let's see what it's mentioned here that CH alpha tail, CH delta E and CH delta T are all negative. Let's see how we get negative. Okay, so now this is your hinge point. And let's suppose the center of pressure is somewhere here. Now, if your tail is seeing an angle of attack, alpha tail, if initially, let's just start. Okay, if initially your velocity was here, alpha tail is 0. Right? So there is no lift produced at the elevator. Assume a non-deflected case. So there is no lift produced at the elevator. Now, if the velocity is such way, so as V1, and this is V2, we now have an angle of attack at the tail. So a lift is produced at the center of pressure. Lift is produced at the center of pressure. And so will you have a positive hinge moment or negative hinge moment? Due to this lift, will you have a positive or negative hinge moment?
Negative.
Negative. So you have a pitch down moment. So that is negative. So positive alpha tail gives you a positive hinge moment, which is, it gives you a negative, like that, negative hinge moment, which is why CH alpha tail is negative. Now let's see the effect of elevator deflection. Let me just draw this again. Elevator deflected downwards. This was your hinge. This is your CP. CP, this is a positive elevator deflection. Due to the change in camber, you have again a delta L. Again, the moment seen at the hinge is pitched down, which is negative. You have negative hinge moment for positive delta E. So positive delta E gives you negative hinge moment. So again, CS delta E is negative. Now, what are trim tabs? So it's another portion of the tail, the last portion, something like this. In a freely floating case, if you were not holding the stick, if you were not deflecting the elevator, if you just let it be, the elevator would float upwards or downwards. If I was not deflecting the elevator, if I just let it be, if the pilot is not holding onto the stick, with stick free case, freely floating elevator with an oncoming velocity would be deflected upwards or downwards.
And depends on the direction of air which is hitting the elevator.
Okay, so let's take this condition, then this condition.
It will float upward, ma'am.
It will float upwards. Okay. So let's just draw that. It will float upwards, freely floating elevator. And imagine you have a trim tab. For the freely floating case, it would be something like this. So again, deflection downwards, deflection of the trim tab downwards is positive. So in this case, it is a positive delta T. Now it produces a lift here. Again, it produces a negative hinge moment about the hinge, right? So positive delta T also gives you a negative hinge moment. That is why your CH delta T is also negative. So all of these derivatives, moment derivatives, are negative. CH alpha tail, CH delta E, CH delta T, they're all negative. So like I mentioned before, for a freely floating case, we see that the hinge moment about the hinge is 0. So take CH equal to 0. And just for this, assume CH naught and CH delta tail. Assume there is no trim tab and you don't have a CH naught. If you substitute CH equal to 0, you get your delta E float equation like this. Okay, so it's directly proportional to the angle of attack seen at the tail. This is a negative quantity. This is a negative quantity. So overall, this is the negative quantity for positive alpha tail. Okay. Okay. So now if you wanted your elevator to float at 0 degrees, right? So if you're freely floating condition, if you wanted your elevator to float at 0 degrees, you need your CH alpha tail to be 0. How do you ensure CH alpha tail will be 0? If there is a change in angle of attack, if there's a positive change in angle of attack at the tail, we see that a negative pitching moment is created, like here, right? So for a positive alpha tail, you have a negative moment at the hinge. So this is why your CH alpha tail is negative. If you wanted your CH alpha tail to be 0, what do?
Deflect the trim tab in opposite direction.
if you don't have a trim tab. Like as far as this equation is concerned, we are assuming there is no trim tab. So one way is to have your center of pressure and hinge at the same point. So you make sure that you hinge the elevator at the center of pressure of the elevator. That way, even if there is a lift, since CP and H are in the same position, there is no moment created. Okay, that is one method. Another thing is called horn balance. What is horn balance? Does anybody have an idea?
We have some amount of the control surface ahead of the hinge line.
Exactly, exactly. So you have something, if this is your tail, and you have something like this, right? So this entire thing is deflectable. So this entire thing is your elevator. Now, if your hinge is somewhere here, if this is your hinge line, this is your hinge line, this entire portion, the lift produced by this portion creates a negative hinge moment. But the lift produced by this leading edge portion of the elevator creates a restoring moment. So you design it in such a way that the lift produced by this leading edge elevators and the trailing edge elevators cancel out in such a way that CH alpha tail is 0. Okay, so these are the two methods by which you get CH alpha tail to be 0, so that in a freely floating condition, your elevator floats at 0 degrees. Okay. Okay. Now let's look at some questions. In the figure given below, which aircraft will have higher stability margin? Look at the aircrafts given to you. So the solid line is aircraft A, the dotted line is aircraft B, and they've given you two conditions of CG. One is at 0.25 C bar, one is at 0.35 C bar. Just look at the graph and tell me which one would have a higher stability margin.
Stability margin, it is asking for static margin.
Stability margin, your SM, static margin, yes, static margin. Or which one would have a higher stability? Forget margin, which one would have a higher stability? Which aircraft would have higher stability?
It could be equal or for B.
How will it be equal? Can you try to explain?
These both are different aircraft and both can have different CG position and the neutral point position.
Okay, so why can't it be A? You said either equal or B.
Yes, ma'am, because B is having higher CM naught and a steeper slope.
Does CM not affect stability in any way?
No, ma'am. The CM, the slope determines mainly.
Slope,
The,
yes.
the which one is having steeper slope has the better, higher
Yes.
static margin.
So the answer is B aircraft, right? Both the lines, both the slope lines. So if you just consider for 0.25 C and 0.25 C, that for 0.25 C, B aircraft has a steeper slope. For 0.35 C, also the B aircraft has a steeper slope. Correct? So the aircraft B is more stable, has higher stability, as far as longitudinal static stability is concerned, right? Higher the slope, higher the stability. So aircraft B is having higher stability. Okay. Next question. Which airplane has more control power? What was control power? What was the term that we used?
Tau.
What is tau? What was the equation for tau?
I think CH delta E equal to VH into eta into CL alpha T.
Okay, tau was d delta E upon d alpha tail. This is known as the control surface effectiveness parameter. So this is
Okay, ma'am.
control surface effectiveness.
On control bar, we can say the less deviation in the control surface gives some higher change in the CM. We can say
Yes. So what was that term? You're right. The definition is right. So what was that?
CM delta E.
Exactly. CM delta E. CM delta E, which is dCm upon d delta E. You said it right. So now look at the two graphs and tell me which one would have a higher CM delta E. Just calculate the slopes for the two, not slopes, the CM delta E. Let's do it for the first case. So here, dCm would be 0.2 minus 0.1, and change in delta E would be 10 minus 0. Correct?
I think it will be a graph B.
Yeah. Okay. So what is this value?
0.01.
0.01. And for aircraft B, 0.4 minus 0.2 by 10 is 0.02.
Yes, ma'am.
Yes. So aircraft B has a higher CM delta E. That is, for less deviation in delta E produces more CM, right? So it has a steeper slope with respect to CM and delta E, right? So it has more control power. Do not confuse CM delta E and tau. Tau is control surface effectiveness parameter. CM delta E is the control power, control surface power. Okay. So just calculate these values for the two graphs, and we can see that B has more CM delta E. So it has more control power. Okay. Next question. When an aircraft's trim speed is changed from 60 meter per second to 100 meter per second, maintaining the same altitude, the float elevator will float more or less? Delta E float. So
It will be less, ma'am.
okay. What was the equation for delta E float? Okay, if it is less, you're right. So can you explain your answer?
It depends on angle of attack on tail.
Exactly. It depends on angle of attack on tail. So the equation was,
Reduce the floating angle.
I couldn't hear you. Can you repeat it? Okay, let me just proceed. You can join in whenever you feel you have a justification. Okay. So CH delta E into alpha tail. Now, when I increase the speed, so when I increase the speed, you're maintaining the altitude and all other parameters, your CL trim reduces, right? So how do you reduce your CL trim? So if you have, this is your tail. Now you want to reduce your CL trim. That means the angle of attack at the tail should be reduced, right? So you reduce your CL trim by reducing angle of attack at the tail. That is when you deflect the elevator, but you need to reduce your angle of attack at the tail. So angle of attack at tail reduces, delta E float will be less. Yes?
Yes.
So delta E float is, this is the relation. He is right. It is proportional to it depends on the angle of attack at the tail. So since your angle of attack at the tail reduces, delta E float will be less. Okay. To reduce the floating tendency of an elevator, the hinge line has to be moved aft or forward. If this is your tail, this is your elevator. This is your hinge, this is your CP. So should the hinge be moved aft or forward to reduce the floating tendency of an elevator? We just discussed this. Suppose you want zero floating tendency. What do?
CP and hinge are at same point.
Yes. So you move your H towards CP or you move your CP towards H, right? So that is how you reduce the floating tendency. Now, so they've asked the hinge line has to be moved aft. So if the hinge line is moved aft, at some point, the hinge line becomes CP and the floating tendency is reduced to zero. So as you move your hinge towards CP or as you move your hinge aft, the floating tendency of the elevator is reduced. Correct? Why? Because the moment produced by this lift is reduced. The effect of that lift on the hinge line is reduced as you move your hinge closer to your CP. And if your hinge is at CP, there is absolutely no moment produced and the elevator will float at 0 degrees. Okay. So it is aft. Moving the hinge line aft reduces the floating tendency of the elevator. Okay. Next question. Which of the following is correct for hinge moment? Hinge moment coefficient is a function of tail angle of attack, or is it not dependent on tail angle of attack? Very simple. We just saw this.
Option A.
Depends.
Option A. It is a function of angle of attack. So the equation was CH is CH naught plus CH alpha tail into alpha tail plus CH delta E into delta E plus CH delta T into delta T. So it is dependent on angle of attack of the tail. Now, we've given you this equation for an aircraft. So for an airplane in pull-up maneuver, the following expression was obtained by a student for CG location of 0.3C. So they've given you DFS by DN. Okay, DFS, FS is the stick force, right? Is 120 DCM upon DCL. That is the static margin for a stick-free case. Negative of static margin for stick-free case. So DCM upon DCL for stick-free minus 12. For the airplane, stick-fixed stability margin was 0.25 and stick-free stability margin was 0.2. Okay, this is the information given to you. Now let's look at the questions. How do you find out the stick-free maneuver point? What is stick-free maneuver point? So at what, when some parameter becomes 0, that is known as stick-free maneuver point, just like your neutral point. Neutral point was when DCM upon D alpha became 0. So what should become 0? What derivative should become 0 for your stick-free maneuver point? It is this parameter, right? DFS by DN equal to 0. CG location at which DFS by DN becomes 0. That is your stick-free maneuver point. Okay. So now let's plug that in and try to find this. So DFS by DN, this equation is given to you. Just set it equal to 0. So 0 equals 120 CM on DCL. Stick-free case, we denote it by a dash minus 12. Okay. So what is DCM upon DCL? For a stick-fixed case, we have discussed this. What is stick-fixed case? DCM upon DCL? In terms of neutral point and CG. What was the equation? DCM upon DCL is? is XCG bar minus XNP, correct? In this case, it's tick free, so it's tick free neutral point. Is this clear? Till here, is it clear?
Yes.
Yes.
So now we need the CG location at which your DFS by DN becomes 0 is your stick free maneuver point. So we need to find XCG here. So what else is unknown? XNP bar, that is the stick free neutral point. How do you find out the stick free neutral point? How do you find out X bar NP prime? Look at the values given to you in the question. Let me know how do we do this. They've given you the equation, they've given you the CG location. The current,
We will take the value of that stick free stability margin.
correct. You take stability margin of the stick free case, which is X bar NP prime minus X bar CG. So stick free stability margin is 0.2 X bar P prime minus current CG location is 0.3. 0.3. So X bar NP prime is 0.5. Now plug that in here. You get 120 X bar CG minus 0.5 minus 12 equal to 0. So what is this XCG? This XCG is nothing but your stick free maneuver point. Okay. Maneuver point, CG location at which DFS by DN becomes 0. So what is this value? Just calculate in that equation. Point 0.6. Correct. So that is 0.6. Okay. Next question. Find the CG limits permitted if the magnitude of stick from force per G is to remain within 10 and 30 newtons per G. So your DFS by DN varies from 10 to 30. Okay. So how will you find out the limits? It just says varies from 10 to 30 newtons. It doesn't say if you're pushing your stick or you're pulling your stick. So it varies from minus 10, 10, minus 30, 30. Correct? So what do? You plug in all of those values into this equation. Into this equation, you start from, let's say, start from minus 10. Minus 10 equals 120 X bar CG minus X bar NP prime minus 12 minus 10 equals 120 X bar CG minus X bar NP prime was 0.5 minus 12. So what is the X bar CG for this case? X bar CG for that case?
.6.
Good. It's minus 10. .516, right? Correct? Correct me if I'm wrong. I'll just go to the next value. Next, we take 10. So the extremes we take. Okay, so we take 10, minus 10, 10, 30, minus 30. Okay, so now plug in 10. Rest of the equation remains same. X bar Cg for this case would be 3. We take 30, 20, what will the X bar Cg be here?
Point 85.
0.85.
Sorry,
0.85.
0.8. Last case, minus 30, 120, X bar Cg minus 0.5, minus 12. What will this be? Point 3. So our limits are 0.35 and 0.85. Only one of those values is given here, that is 0.35. Okay, so the extremes are given depending on how much you're permitted to apply, how much stick force you're permitted to apply. Okay, so you have X bar Cg, the two limits here. Only one of them is given in the options, it's 0.35. So when they say it's the magnitude of stick force. Okay, so it doesn't say plus or minus, it doesn't say whether you're pulling or pushing. Okay. Okay. Let's go to the next question. The hinge moment characteristics of the horizontal tail of an airplane are given as follows. CH alpha tail, CH delta E, CH delta T. Obtain the floating angle of elevator for alpha tail 5 degrees and assume the trim tab angle to be 4 degrees. We can see here that all of these parameters, all of these derivatives are negative. So all of them have this negative sign, just like we'd seen in the first slide. So it's a simple calculation. What was the equation for hinge moment? CH is, assuming no
CH naught plus
yes, okay.
CH delta E into delta E.
Okay. Yes, you're right. Continue.
CH alpha T into alpha T.
And CH delta T into delta.
Delta T.
Now for the stick free case, and assume this to be 0. Stick free case, CH is 0. So I tried 0. CH delta E into delta E free plus CH alpha T into alpha T plus CH delta T into delta T. So plug in all the values and let me know what delta E free is. Delta E free or delta E float, at which point the hinge moment becomes 0. What is the value? CH alpha tail is 0.003 into alpha tail is 5 plus CH delta tail is 0.003 into 4 divided by CH delta E is minus 0.0055. It's minus 0.49, correct? Are all of you getting this?
Yes, ma'am.
So it's minus 0.49 degrees. So is the elevator floating down or up?
Up.
Up, correct. So elevator floating up is negative and down is positive. Okay. Okay. Now this question for an airplane, they've given you W by S and they've given you the density at the altitude. They're giving you some values here. This is wrong. Pull is negative. When you pull, our convention is that pulling the stick is negative, pushing is positive. Okay. Okay. So now they're giving you the various velocities at which it's flying and the stick force. This is the stick force. Okay. And now they've asked you to find out the stick free neutral point. Just look at the question, see what data is given to you, and try to tell me how to proceed. So they've given you 3 velocities at which it's flying and the stick force applied at 2 different CG locations for each of these velocities. Okay, so stick free neutral point is when BFS is the CG location at which BFS by Q by DCL becomes 0. This is the definition of the stick-free neutral point. This X in P bar prime. So from the given data, how do you think we should proceed? So in this, we have Fs. We need to find out CL and Q, and then maybe we can try to find the slope, correct? So let's just make one table here. V, CL, below. Q, S1. This is Fs1 and this is Fs2. Okay. Fs1 by Q, Fs2, Fs2 by Q. Let's just have those 3 velocities. So the first velocity is 50. How do you find out CL? CL is
2W by S into G 1 rho V square.
rho V square. Yes. So just substitute the parameters and tell me what will be the CL for the first case. W by S is given to you. They've given you density. And V is 50.
Worst case, it's 0.4.
0.4. What about Q? Q is half rho v square. Here it is 1000. So FS1 here, pull is negative. So FS1 is minus 2. And FS1 by Q is divide minus 2 by 1000. The minus FS2 is plus or minus 1.
Yes.
Still pull, right? Pull is negative. So negative 1. So here you have negative 0.001. Now let's do it for the next case. 57.3. How much will CL be?
Point 3.
Q. What is FS1 for this case?
0.
Now for the last case, 17.71. CL is what about Q?
One 999.96.
So let's just take it 2000. FS1
Positive
four.
4.
So that is 4 by 2000, that is 0.002. Plus 2 is 2 and 0.001. Okay. So now what we do is we find out the slopes. So we take dFS1 by dCL. So take any 2 points. Let's take the first and last point. So what is the slope here? Is minus 0.002 minus 0.002 by dCL. That is 0.4 minus 0.2. What is this value? .02. Similarly, do it for the other case, dFS2 by Q by dCL. This minus 0.001 minus 1 by 1. That is 0.01. So what we see here, let's just draw this graph. Is dFS Q and this is CL. So for the first case, you have something like this. The second case, you have something like this. Right? So this is for 0.2 CG. This is for 0.25 CG. Right? So now we need to see the neutral point. What is the neutral point? Neutral point is where dFS by dQ upon dCL becomes 0. Right? The CG location where this value becomes 0. So what do we have to do? What graph do we have to plot now? Let's just erase these values. Let's erase this graph as well. So now how do we proceed? We have these two slopes. How do we proceed? It's the value where value of CG where the slope becomes 0. Right? So what is the graph that we have to draw? What is on the y-axis? What is on the x-axis? Try to think.
On the x-axis, we will take the CL values, and on the y-axis, we will take the FS by Q.
You're not audible. I can't hear you.
Ma'am, for the x-axis, we will take the values of CL,
Okay.
and for the y-axis, we will take the values of FS by Q.
Okay. So that is the graph that we just drew, right? So that is DFS by Q. Sorry, FS by Q. And this is CL. We got something like this.
Yes, ma'am.
So how will we try to find out the neutral point from here?
And the point where FS is 0.
The FS becomes 0 here also, right? Even if I were to take FS becomes 0, how do you find out the CG location? You only get CL, correct? How do you find out CG? So neutral point is where the CG is the CG location where DFS by Q by DCL becomes 0. You have all the data you need. You just need to formulate. It's a graph. Just try to think about it. The x-axis and y-axis are not these. What would it be?
Ma'am, we can use the value of DFS by Q by DCL. We equate it to X NP prime minus XCG. Can we use that for that static margin formula?
In the static margin, where will this term come? This doesn't come, right?
Okay, that is DFS by DN.
Yes. Okay, so let me just tell you, this is FS or DFS by Q by DCL. And on the x-axis, you have CG locations. Okay. So let's take, this is 0.2, this is 0.25. 2.25, and our two slopes were minus points. We have minus 0.0001 and 0.02. So for the 0.2 CG, you had this, and for 0.25 CG, you had this. You just join this line, extrapolate it, and this is the CG location where your DFS by Q by DCL becomes 0. Correct? How do you find out this equation? It's the equation of a straight line, just extrapolate it to the 0. So let me erase all this. So BFS2 Q by DCL is minus 0.01. Okay. So now for this graph, let's just take the equation of a straight line. So you have y2 minus y by y2 minus y1. So the 3 points, this is point number 2, this is 1, and this is denoted by x comma y. is x2 minus x by x2 minus x1. So we need to find out x, y is 0, correct? This y is 0. So substitute all the values here. Y2 is minus 0.02 minus 0 minus 0.02 minus y1 is equal to x2 is 0.2 minus 0.6 by 2 is 0.25. So what is the value of x? Okay, this is 0.25. Okay, what is the value of x? It's to 0.3. Yes. So that is the CG location where DFS by Q by DCL becomes 0. Okay. So I've just written a simple MATLAB code. I'll just show you. Just a minute. Okay, 1 minute. I'll have to show you the plots as well. Are you able to see the code?
Yes, ma'am.
So I just initialized the velocities. I calculated the Q for each of those. I calculated the CL. This is just what we have done in the table format. I've just written the code. Calculated FS1. I've taken FS1 from the equation and plotted two figures. The first figure is what we had drawn initially. Okay. Able to see the figure, 1 minute. Okay, so this is the first figure, which is Fs by Q versus CL. Okay, so the blue line is for 0.2 xCg and red line is for 0.25 xCg. So we can see the two slopes. Next, I take this plot. This is DFS by Q by DCL, and on the x-axis you have xCg values. So the first point was 0.002 for 0.2 CG location. Next is 0.01 for 0.25 CG location. And then if you extrapolate it, you get the next value. So that is 0.3 xCg location, where this becomes 0 is 0.3. Okay. Do you understand this question?
Yes, ma'am.
Yes.
So let us go back to our slides. Okay, so the value where that becomes 0 is 0.3. Now let's go to the next question. So this is the data that is given to you. Just look at all the data that is given to you. You have the CG location, the weight of the aircraft is given to you, aspect ratio of the wing, wing span, mean aerodynamic chord of the wing, aspect ratio of the tail, tail span, alpha naught, wing setting angle, tail setting angle, lift curve slopes of the wing and tail, the moment arm LT, elevator area, elevator chord, delta E naught, the elevator effectiveness parameter, that is tau. We have seen this control surface effectiveness parameter. You have the slope of the downwash angle, the tail efficiency factor, and you have your 3 gradients here, assuming CS not to be 0. Now let's look at the questions. Okay, they've given you a graph, the CM versus CL graph obtained for elevator fixed and elevator free case. Fixed and free. So from this, can you tell me if the elevator fixed is stable or is more stable, or elevator free is more stable? Which is more stable?
Fixed.
Fixed is more stable because its slope is steeper. Okay. Okay. Now let's look at the questions. Find the stick fixed neutral point. The graph is CM versus CL. They've asked you to find out the neutral point. How do we do this? How do we do this? It's straightforward. Just take the slope of the graph. So, what is it? Minus dCm by dCl is x bar NP minus x bar CG. Right? So, what is dCm upon dCl for stick fixed case? Take any 2 points and tell me stick fixed is this, the bottom line. What is the slope? Take these 2 points, this and this. What is the CM at this point?
Point 0.05.
0.5. CM at this point is 0. CL at this point is 0.3. 3 minus 0.8 is equal to x bar NP minus x bar CG is given in the question 30%, so 0.3. So that's 0.3. Now, how much is x bar NP?
Minus 0.1 plus
How much?
minus of 0.1 plus 0.3.
0.2.
It's 0.4, right?
Yeah, okay. Minus will get it. Yes.
Yes. So it's 0.4. So that is 40% of mean aerodynamic chord. Now let's do it for the stick free case. Same thing for the stick free case. So it will be, okay, some chat message. How do we calculate? Okay, let's get back to this question later. Okay. For the stick free case, minus dCm by dCl free is x bar NP free minus x bar CG. So now we take this line. The slope will be 0.05. Again, this point and this point minus 0. And what are the lifts at those points? This is same 0.3. This is 1. Correct? Is x bar NP dash minus x bar CG, that is 0.3. So what is x bar N?
0.37. Point 37.
Sorry about that. I think my internet connection was poor. Let's get back to the question. Yeah. How do you find out wing area? I hope I'm audible now, right?
Yes, ma'am.
Okay. So how do you find out the wing area?
Span into wings.
I couldn't hear you. What into?
Wingspan into the wing MAC.
So you have aspect ratio of the wing is PS. So aspect ratio of the wing is 6 and wingspan is 6 square. So you can find out the area of the wing, which is 6, right? Right. Next, what is the indicated trim airspeed for stick fixed case? What is the indicated airspeed for stick fixed case? How do you find out the velocity? Velocity, it's just directly, just take it directly. So that lift equation again. Rho v square SCL. So v is square root of 2w by s. What's it? 2w by s rho CL. Substitute the values directly and just let me know. 2 into 700.81. S was 6. Rho is 1. 5. CL is 0.8. What is the value?
48.
48. So that is this. Next, find out the tail volume ratio. What was the formula for tail volume ratio?
Area of tail into LT upon area of wing into chord.
So we need to find out the area of the tail for this case, similar to area of the wing. Take the aspect ratio of the tail, ET square by ST. Aspect ratio of the tail is 4. Span is 2 square by ST. So ST is 1. Plug it in here, you have 1. Moment arm is given to you in the question, 6.5. Wing area, we've calculated it to be 6. Mean aerodynamic chord of wing is 1.2. So how much is VH?
And 9.
0.9. That is 0.903. Value of Cm delta E in per degree. What was the equation for Cm delta E? Is minus eta EH CL alpha of tail and tau. How do we calculate this? Tell me.
Minus 0.9
It's 0.9.
into 0.9 again.
VH was how much?
No,
0.9. Into
0.1.
0.1 into
0.4.
4. Is this correct?
I think we need to convert 0.1 into radians.
They've asked you in per degree, so that is fine. So it's fine. This is dimensionless, this is dimensionless, this is dimensionless. Only this is there, this is in per degree. So you don't have to convert it into per radians. That is all right. Is anything else wrong with this? Is this correct?
Yes, ma'am, it is correct.
Okay. They have given you the lift curve slope.
CL alpha is, you have to convert it in 3D, I guess.
Yes, they've given you for airfoil. You need to take it for the wing. So CL alpha tail 3D, CL alpha tail 2D by 1 plus CL alpha tail 2D by pi EAR. Here of the tail. So let me know what are the values. You need the CL alpha 3D finally to be in per degrees. Okay, per degrees, because you need your answer to be in per degrees, and this will be in per degrees. So accordingly, tell me the values.
So 0.1 upon
Yes. Upon
0.1. So
0.1. Here in this term, CL alpha tail 2D should be in per radians because this entire thing should be dimensionless. Should be dimensionless. Only this term should have a dimension which is in per degrees. That is already taken care of. This should be dimensionless. So your CL alpha 2D has to be in per radians. Okay. So you have to multiply. What was the value? 180 by pi.
100. Yes.
By pi E, take E as 1 if it's not given. Pi E AR, AR of tail. It's 4. So what is this value?
Zero 0.06.
0.068 per degree. Okay. So this is the value that you need to plug in here. So it is not 0.1, it is 0.068. So how much is CM delta E? Minus.
Ma'am, VH is 40.403.
Sorry, that is 9. Sorry about that. In the previous question it was 903.
0.022 I'm getting.
0.0.
It's minus 0.0223.
Correct. So that is the right answer. So you need to be very careful about what lift curve slope is given in the question and convert it to the wing, that is 3D. Okay. So with this, we come to an end of today's session. Does anybody have any questions? There was a question in the chat box. No. Okay, I can't find it. Does anybody have any doubts? Any questions?
Yes, ma'am. I've actually wanted to ask when will the admit card will be available to us?
I'm not sure about that. You can ask that in the forum.
Okay, ma'am.
Anything else?
Ma'am, in week 12 assignment, ma'am.
Okay, that we'll discuss next Tuesday. Week 12 assignment will be after that, right?
Yes, ma'am.
We have 2 more weeks before your exam, so we can discuss that then.
Okay, ma'am.
Anything else? Okay. If not, then we'll end the session. We'll meet again next Tuesday.
Okay, thank you.
Yeah, man.
Thank you.